Hello and welcome to today's session of Basic Electrical Circuits. Today we will be studying analogous systems. So, what do we mean by analogous systems? So, in basic electrical circuits, we have learned how to deal with electrical circuits and networks and devices that uh, devices that come in electrical networks like capacitors, resistors, sources, and loads, how to deal with them. But these concepts can be extended further to other disciplines as well. So, when we uh, consider those disciplines and we want to apply these concepts of electrical circuits, so then just we just convert those s- uh, models or those circuit not circuits, those models or systems into analogous systems in the electrical domain. So those now these converted systems that are there in the electrical domain are known as the analogous systems. So one of the most important tasks in the analysis and design of control system is the mathematical modeling of the system. So whenever we have a system, suppose this is our system, we need to mathematically model it. We know that this is x, so that we can know for what input, that is the x is my input. We obtain a output y, right? So for that, what we require is a mathematical model of the system. So the two most common methods of modeling linear system are the transfer function method that we have already seen, and a state variable method that has been covered in the that will be covered in the next week's course, I guess. So there are two ways of modeling this linear system. So linear system we have talked about in electrical domain, but in any domain we can have linear systems, and those can be realized using either transfer function method or the state variable method. So the transfer function method is valid only for linear time invariant systems, whereas state equation method are valid for both linear as well as non-linear systems. Okay, so transfer function method has some limitations. What are they? So transfer function method has some limitations. Firstly, they are applicable. They are applicable in linear time invariant systems. So basically the coefficients of the state matrix, the coefficients of the state matrix will be time invariant. They won't vary with time. And secondly, the initial condition of the system must be relaxed. That is, the initial condition of the initial condition of system. It won't be a system. It will be state. The initial condition of the state must be relaxed. Okay. So a control system may be composed of various components. So control system can compose of, it can may be composed of mechanical components, it can be of thermal components, fluid, pneumatics means air, which deals with air pressure and all, and electrical sensors and actuators, anything. So in this module we review the basic properties of these dynamic systems, and we will be going through the modeling of those systems. So firstly, we will go for modeling of mechanical systems. So uh, mechanical systems we are modeling, but we at the end of when we want to analyze the systems, we will always convert them into their analogous electrical system. Hence, the name of this course is name of this module is analogous systems. So mechanical systems may be modeled as systems of lumped masses or distributed mass systems, similar to electrical, where we can have a lumped model or a distributed model. In mechanical also we can have a lumped model or a distributed model. So wherever when we have a lumped model, so in case of lumped model, what happens is we have a continuous m mass. But in case of distributed model, we have some m by x mass per unit length into dx integral. So it's distributed over the length, suppose. So whenever we need to find the entire mass, we need to do an integral of m by x into dx. So we will get then we will get the mass. This is the difference between the lumped model and a distributed model. Distributed models are modeled by partial differential equation. Usually they are modeled using partial differential equation, whereas lumped models are modeled using ordinary differential equation. Since you can very well understand that since lumped model is represented using ordinary differential equation and distributed model is represented using partial differential equation, partial solving partial differential equation is quite hard compared to ordinary differential equations. So we always choose to make a lumped model so that we can solve it easily using ordinary differential equation. So in reality, all the systems are actually continuous, but it is easier to approximate them with lumped mass model, as I just said, and hence we can solve it using ordinary differential equation methods. So what do we mean by mass? Mass is considered a property of an element that stores the kinetic energy of a translational motion. So mass is in simpler terms, this is the basic definition. Mass is considered a property of element that stores the kinetic energy of translational motion. But in simpler terms, mass is equivalent to inertia. Now we come to the analogous representation. What can be mass modeled as? What does which component shows inertia in electric circuits? It is none other than the inductance. So if we consider voltage to be the source, then and current to be the response, the inductance doesn't allow the change of response quickly at a sudden. So that's what is done by inertia. A body tends to remain in its inertia of state or in its inertia of motion until the force is applied to it. Newton's first law. So mass is basically inertia. Hence, the analogous representation of mass is the inductance of the electric network. So this thing you already know that mass is equal to weight by the acceleration due to gravity, where acceleration is due to gravity is considered to be 9.8066 meter per second square. So the equations of linear mechanical systems are written by first constructing a model of the system, connecting the interconnected linear elements, and then by applying Newton's law of motion on what we have done in class 11 and 12 free body diagram. So if we have a body, we represent it like a square and we write the mass on it, and we point out all the forces that are applied on it, such as F1 is on the on up direction, F2 is downward, let's say F3 is being applied rightward, and F4 is being applied. So this is a free body diagram, FBD of this body M of mass M. So we will be utilizing this to analyze all the mechanical systems. So the motion of mechanical elements can be described in various dimensions as translational, rotational, or a combination of both. The equations governing the motion of mechanical systems are directly or indirectly formulated using Newton's laws of motion. What are the Newton's laws of motion? Firstly, it a body chooses to stay in its inertia of motion or its inertia of rest until and until the force is applied on it. Second is uh, force is equals to mass into acceleration. And third is every action has its equal and opposite reaction. F1 is equals to F2. These three uh, Newton's laws will help us in forming the equations that will govern the motion of the mechanical systems. So, translational motion. The motion of translation is defined as a motion that takes place along a straight or curved path. So, the variables that are used to describe translational motion are basically displacement, velocity, and acceleration. So, as stated by Newton's second law, we can say all the external summation of all the external forces on a rigid body is equals to mass into acceleration. So here we have a body M. It has a displacement in the right direction and a force of Ft is being applied on it. So basically Ft equals to m into a. Now what is acceleration? Acceleration is m d2y by dt, double derivative of displacement, and I can write it in this form. This motion of this force which occurs in the body due to its motion, we term it to be inertia force. Inertial force. Next we come to spring. So a linear spring is a model of an actual spring or a compliance of a cable or belt. So it is considered as an element. So spring is considered, this is a very important line. Spring is considered as an element that stores potential energy. So it stores the potential energy. So as it is compressed or it is expanded, so it stores the potential energy, and as it is released, it gives back the potential energy to the body attached to it. So the equation of spring is simply given by the linear spring is Ft equals to K, which is the spring constant, times the displacement Yt, where K is spring constant. It shows basically the stiffness of the spring or the amount of deformation that it can take per amount of deformation it can take to store some amount of energy. So this is the model of a linear spring, and this is the expression where the displacement and the force is proportional to each other. So next comes friction for translational motion. So whenever there is a motion or tendency of motion between two physical elements, frictional forces will occur for sure. So frictional forces are usually nonlinear in nature. So the characteristic of the frictional forces between two contacting surfaces often depend on such factors as the composition of the surfaces, the pressure between the surfaces, and their relative velocity, among others. So, an exact mathematical description of frictional force is highly difficult because when it's stopped, it has the static friction. When it's moving, it has a dynamic friction. Both are different. So different types of friction that come up are viscous friction, static friction, Coulomb friction, um, and these three are the most practical friction that we encounter. So yeah, viscous friction. So viscous friction is when we have a damper or a damper kind of arrangement. This is a damper kind of arrangement but here this is the piston, and here we have air. So if we apply a force, so it will try to damp out its movement, so it's directly proportional. So here the force is directly proportional to the velocity of the mass that is connected here. Hence the expression or for a damper or a viscous friction is Ft equals to some constant B into dy by dt, where B is viscous frictional coefficient or damper coefficient. Yeah, Static friction is basically a kind of friction that comes at the beginning when the body is static. So it is a friction that avoids it to move even though a force is being applied on it. So when the force exceeds the static frictional force, then only the body comes into motion. And when the body comes into motion, then the dynamic friction comes to play. And the sign of the friction will be the direction of basically the direction of the motion or the initial direction of the velocity. And the other friction, that is the Coulomb friction, it is a constant kind of friction, and it is basically retarding force that has a constant amplitude with respect to the change of velocity. So it's the sign of the frictional force changes with the reversal of the direction of velocity. So these are the basic units of what we have come across. So mass, the analogous, yeah, mass reference inertia, the analogous electrical quantity will be inductance. We are applying displacement or a distance, rather it should be displacement. Here it is written distance. So we are applying a distance or displacement. So we represent it using voltage. It's analogous to voltage rather. Velocity is the rate of change of voltage. So it can be considered to be again uh, analogous rather to current. And acceleration can be again considered acceleration basically force. Oh, my bad. So the voltage is the source, right? So what is the source in a mechanical system? It is the force. So here it will be voltage analogous to force. Acceleration is basically uh, voltage by inertia. Distance, the velocity can be considered to be the current. Spring constant, it can be considered to be 1 by the capacitance. Damper, by the name you can see damper coefficient or viscous friction coefficient. In electrical domain there is one thing, resistance. These are the analogous components. So now we can consider an example of a mass spring damper or mass free friction system, and we can do the free body diagram of this body. So here is my body, mass m. So this is the direction of its movement on this direction, yt. The force applied is Ft, which is known as the inertial force. Inertial force. So here is the spring. So it applies a force in this direction with the spring constant into the displacement yt. And another is the damper coefficient v is proportional to the speed, so dy by dt. So we can write an expression doing the balancing, we can write the expression as ft, uh, just a second, yeah, am d2y by dt2, this is the inertial force. So we can now, this is the force that is being applied, ft. So hence we can say from here only, ft minus. So this is the direction. So inertial force will always have a tendency to go in the other direction. So ft will be equals to m d2y by dt2 plus b dy by dt plus k. The expression. So from this expression we can rearrange the terms and write it in this form. d2y dt2 equals to minus b by m dy by dt minus k by m yt plus 1 by m ft. Where ft is the, this is the forcing function or the source. Now as we said, to find a transfer function we require zero initial condition, and with that we obtain this transfer function. To converting everything into Laplace domain, we obtain this transfer function. So now it can be represented in terms of block diagram as shown here. So the force Fs is being applied, and so y dot t. So to write this expression, we can do it in this format. Let's, so we have d2y by dt2 is equal to minus b by m dy by dt minus k by m, sorry, y plus 1 by m uh, ft. So now we can write the expression as follows. Let um, y1 equals to y, y2 equals, not y, it should be x. X1 is this, x2 is y dot. I can write the expression as x1 x2 x1 dot x2 dot equals to y dot, that's x2, it will be 0 1, and x2 dot is y double dot, which is this, which is written as minus b by m x2 minus k by m x1 plus 1 by m ft. So from here I can write this to be minus k by m minus b by m x1 x2 plus 0 1 by m f of t. This is my state space representation. So this can be represented in terms of x dot, is x dot into equals to a into x plus b times u, where input is the force ft. From here only we can draw this block diagram, and as we have found out, this is the state space representation also from here. And from here also we can apply zero initial conditions and then find the transfer function between ys, that is Laplace transform of the displacement, and the Laplace transform of the force fs, ys being the output, fs being the input, and we can find the block diagram accordingly. Now if we incorporate the initial condition, then the expression of ys will look something like 1 by ms square. This is the from the transfer function, and then we will incorporate x10 and x20, which are the displacement at t equals 0 or speed at t equals 0, and we can get this is the whole expression for the output of the displacement at, in the Laplace domain. Then we can do inverse Laplace, and we can obtain the displacement at any particular time. So this we have concluded the translational motion. Next is the rotational motion. So in rotational motion, the of a body can be defined as motion about a fixed axis. So here we have a fixed axis. So initially we consider translational motion, where we had a body m. So it has a movement in either direction, in in forward direction or in backward direction. So this is a translational motion. It will move, all the points will if it moves some, say somewhere at this position, all of its point will have the same amount of displacement. But in rotational motion, that's not true. In rotational motion, there may be a point which does not experience any displacement at all, and there may be another point that can experience a tremendous displacement. Suppose this state, it has moved to this portion. This point hasn't experienced any displacement, whereas this above point has experienced this much displacement. So this kind of systems are known as rotational systems. So rotational motion of a body can be defined by motion of a body around a fixed axis. So this point is the fixed axis. So the extension of Newton's law of motion can be done in case of rotational motions. So here in Newton's in case of translational system, we said that summation of forces is equals to F, which is equals to m into a. Here we say summation of torques equals T, that is equals to J times alpha, where J is the moment of inertia. So here it is also inertia, so it will be represented using inductance. And alpha is the angular acceleration. Angular acceleration. So here we have angular velocity omega and angular displacement theta as well. And the forcing function was In translational motion it was force, here it will be torque. That's only the difference. The analysis remains exactly the same. So here also, there we used to write the forcing function Ft is equals to the inertial force m d2y by dt2 plus b, there is a damper dy by dt plus spring ky. Here we will write the torque, forcing function is torque, is equals to the inertial angular inertial force, that is angular inertial torque, that is j d2 theta by dt2. Similar, totally similar. Here is y is displacement, theta is angular displacement. If we have a let's say rotational damper arrangement, so it will also have a constant, let's say b, again b2, so d theta by dt. And if it has an angular spring, then we will have some k2 theta. So this is the similar representation can be formed in case of rotational system as we have done in case of translational system. Torsional spring, it will also have a linear expression like the torque equals to k into theta, as we have already discussed. Viscous friction can be considered b into d theta by dt. So this is inertia, angular, and these are similar expressions, and similar representation can be formed. This is an example of a motor coupled to a inertial load through a shaft with a spring constant k. Uh, Non-rigid coupling is being made between the two mechanical components. So it often causes torsional resonances that can be transmitted to all parts of the system. How does that happen? TMT is the motor torque, BM is the motor viscous friction coefficient, obviously torsional. K is the spring constant of the shaft. Shaft has some torsional spring constant. Theta mt is the motor displacement, omega mt is the motor velocity, Jm is motor inertia, theta lt is load displacement, omega lt is load velocity, Jl is the load inertia. So the expressions can be written as in this form, similar expressions. So these equations can be written where this is basically the d theta d2 theta by dt2 equals to b by j. There is to be b by m, b by j d theta m by dt minus k by jm. Since load torque is load displacement theta is considered uh, yeah, load displacement with respect to motor is considered to be constant. So it doesn't appear in this expression except for the spring term k by jm with theta mt minus theta lt. Again, we consider in terms of load, then we can write, since there is no what should I say? There is no torque, not torque, torsional viscous friction. So you can directly say k theta mt minus theta lt. This is jl d2 theta lt. Right? This in terms of load, this in terms of the motor. So now arranging them and writing expressions, we can form this signal flow graph. And from this signal flow graph, using Mason's gain formula, we can obtain a relationship between, let's say, theta ls and by tms. We can obtain a transfer function considering zero initial conditions. We can find the transfer function for this. That's it for today. And if you have any doubt, please do ask in the comment section. And thank you.